Welcome to my project, Space Shuttle Liftoff. For my specific problem, I worked with a rocket ship exiting Earth. The space shuttle's mass that I used was 2,027,557.9 kilograms. We're assuming that the space shuttle has a uniform acceleration, which means that it also has a velocity that increases at a constant acceleration. It works this way because as the shuttle uses up fuel, it loses mass, which makes the shuttle accelerate. I also worked with escape velocity, which is the velocity that an object needs to achieve before reaching orbit so it isn't pulled back by Earth's gravitational pull. How do we know escape velocity? Scientists use Newton's universal law of gravitation to get an equation that, when solved, you get an answer of 11.2 kilometers per second, which is Earth's escape velocity. So the question was, how long does it take a space shuttle to travel a minimum distance of 100,000 meters or 100 kilometers, which is Earth's altitude, if it has an initial velocity of 0 meters per second at liftoff and a final velocity of 11,200 meters per second, which is escape velocity? To answer this question, I created a velocity time graph and an acceleration time graph. On the first graph, we know that the initial velocity is 0 and the final velocity is 11,200 meters per second, which will make the graph look like a triangle. Since we know that the area has to be 100,000 meters, we can go ahead and use the area for a triangle formula to solve for time. Since acceleration is constant, the shape will be a rectangle, but we'll come back to this later since we don't have any of the variables. When solving for time, we set 100,000 equal to 1/2 times 11,200 t. The answer we get is 17.86 seconds, which is the time it takes to travel. After we have time, we can put it in the graph, and finally, use the slope formula to calculate acceleration. We have 11,200 over 17.86, and the answer is 627.1 meters per second squared. So that is our acceleration. So the shuttle takes 17.86 seconds to travel a distance of 100 kilometers at a final velocity of 11.2 kilometers per second. Since it's always useful to have more information, I decided to create an ID, FBD, and VAD to show the unbalanced forces. I know that it's unbalanced because there's uniform acceleration and not constant velocity. The FAD and VAD will have 3 arrows, the force of thrust being greater than the gravitational force for it to escape Earth's pull. I calculated Fnet using the formula of mass times acceleration and got that it's 1,271,481.56 newtons. I also calculated gravitational force and force of drag, and the thrust of the engines was actually given, and it was 30,160 kilonewtons.